All right, good morning. You came back again. That means you're not learning anything, okay? But welcome back. Have the lights down a little bit, please. We are in week 3, and in week 3 we're going to talk about what we know about planets around other stars. In week 1 we talked about the history of what people have thought about life in the universe, and last week we discussed the techniques that astronomers have developed for detecting planets around other stars. And this week we're going to talk about what the evidence is for those actual planets. So here we go. Excuse me. For those of you who have been sleeping under a rock for the last 10, 15, however many years, last September, you might have missed this news release, September 30th, 2014. Astronomers find cousin planets around twin stars. This was an announcement by some European astronomers that they'd found 2 planets that are like Jupiter, so-called Jupiter-sized planets, in orbit around each of 2 stars in a binary star system. So a binary star system has 2 stars orbiting each other. And in this star system, there is 1 planet orbiting each of those 2 stars. Those stars have the fancy names 94, WASP 94A and WASP 94B. On the names of stars, the capital A designates a star. The capital B designates a star. So if you have a capital A and a capital B in a star system, you have a binary star system. A little a, you'll notice today, designates a planet in a star-planet system. All right. So this was news because some astronomers were worried, if you will, that maybe in binary star systems, planets might have a hard time forming. So this suggests that maybe it's not so hard to have planets in binary star systems. In any case, last September 30th, big news, planets discovered. If you missed that one, January 6th, 2015, this year, in the New York Times, the headline, "As ranks of Goldilocks planets grow, astronomers consider what's next." By the way, these are not actual pictures of the planets. These are cartoons. These are sketches. We have not taken photographs of these planets. Astronomers announced they had found 8 new planets orbiting their stars at distances compatible with liquid water, bringing the total number of potentially habitable Goldilocks planets to a few dozen. Goldilocks planets would be planets living in the right place, where it's just right to have liquid water. 8 planets, January 6th. If you missed that one, January 7th, Kepler 438b, notice the little b means a planet. 438b isn't Earth's twin. There are more habitable planets out there. The Kepler Space Telescope confirmed its 1,000th planet discovery. That's why it was big news on January 7th, because the Kepler Space Telescope now had discovered 1,000 planets around other stars. And according to this news release, Kepler 438b was named the most Earth-like planet yet found. All right, if you missed that one, January 27th, ancient star system reveals Earth-sized planets forming near start of the universe. You might have missed this one because this was from the Astrophysical Journal, and my bet is most of you weren't reading the Astrophysical Journal on January 27th. This stuff just isn't news anymore, folks. It doesn't even make the New York Times. But this was interesting, at least to astronomers, because this planet was found on around a very old star, a star that's 11.2 billion years old. And some astronomers thought that stars this old might not have planets because the material was like carbon and oxygen and iron and magnesium, out of which a planet like the Earth is formed, might not have even existed when the universe was that young. But here we've got a planet around an old star. And in case you missed that one, well, March 4th, 2015, This was just in a news release. It never even made the newspapers. A 10 Jupiter-mass planet found in stable orbit in a quadruple star system. So we got 1, 2, 3, 4 stars, and we've got a planet somehow managing to orbit one of the stars in this quadruple star system. It's not news anymore. So, January 1st of this year, astronomers knew of 1,861 planets that had been confirmed, not suspected, but confirmed in orbit around other stars. March 23rd, now that's a couple days ago now. I know it's kind of old news. But according to the website exoplanet.eu, there were 1,901 known planets around other stars. So in about 80 days of the calendar year 2015, astronomers had added 40 new stars in about 80 days. Every 2 days, another star, another planet. The number of planets is growing fast. Right? So let's talk about some of those planets. The first regular planet discovered around another regular star, a star like the Sun, was discovered around the star known as 51 Pegasus. The planet is called 51 Pegasus b. Doesn't get a fancy name. The star 51 Pegasus is at a distance of about 51 light years, which means it's relatively close to the Sun. A Sun-like star means the mass of the star is about the same as the mass of the Sun. This star has a mass of 1.06 solar masses, so it's 6% more massive than the Sun. Its temperature is about the same as the Sun, 5,600 kelvins, so it's 4% lower in temperature than the temperature of the Sun. The first astronomers looking for planets decided that their target stars should be stars that were as Sun-like as possible. So stars that had nearly the same mass, nearly the same temperature, and therefore nearly the same brightness or luminosity as the Sun. And this planet was in the Great Square of Pegasus, so it's right over here. Just an ordinary star. And the evidence for the existence of this planet, again, this is not a picture of the planet on the right, but the evidence for the existence of this planet is in this plot. And what you're seeing in this plot, the vertical axis is velocity. The horizontal axis is time in days. So it goes from 2, 3, 4, 5, 6 days. So this spans about 4 days. And you're seeing the velocity of the star. Remember, we talked about radial velocity for the detection of planets. And you're seeing the star come toward you, and then away from you, and then toward you again. And you're seeing the star in orbit around something. And based on the speed, the velocity of the star in its orbit, and the size of the orbit, we can calculate the mass of the thing that's making the star orbit. And the mass of that thing is a planet like Jupiter. So this planet has a mass of 47% the mass of Jupiter, 0.47 Jupiters. So this planet is known as a Jupiter. Okay? Fancy name. It's a Jupiter-like planet. It orbits this star at a distance of 5% of the distance of the Earth from the Sun. So you need to know a buzzword here because it helps us have the conversation. What astronomers call an astronomical unit, or an AU, this unit right here, an astronomical unit is the distance of the Earth from the Sun. So if you think of the Earth's orbit as simply being a circle, the radius of the circle would be 1 astronomical unit. The Earth's orbit isn't exactly a circle, but it's close enough to a circle that we can think of it that way. And the average distance is 1 astronomical unit. 93 million miles, 150 million kilometers. Instead of thinking in miles or kilometers, it's just 1 astronomical unit. This planet is 5% of that distance. This planet's very close to the star. The speed with which a planet orbits its star depends on how close it is to the star. The closer the planet is to the star, the faster it orbits. This planet's close to the star, so it orbits fast. It orbits in 4.2 days. 4.25 days. That's our days. Those are 24-hour days. Yeah. So 4 times 24 hours times 0.23 times 24 hours, they're hour days. Quickly. At this distance, this planet's hot. So this planet is known as a hot Jupiter. So more buzzwords for you. You can remember this one. Hot Jupiters. There are a whole class of planets known as hot Jupiters. Hot Jupiters are planets which are big, like Jupiter, which are in very small orbits, and as a result, they're very close to their stars. They're simply known as hot Jupiters. About how many of those 1,900 planets are hot Jupiters? A third to half of them. I don't have an exact number, but an awful lot of them. Hot Jupiters are the easiest planets to detect because hot Jupiters, because they're close to their stars, have the biggest effect on their stars in terms of tugging on their stars and making the stars move. Because they're close to their stars, they block more light of the star. So in terms of transits, they're easier to detect than little stars. So hot Jupiters are the easiest planets to detect. 51 Pegasus, 1995. Here's another hot Jupiter. I'm sorry. This is still 51 Pegasus. In terms of thinking of Jupiter as a cartoon, here's the Jupiter in distance from the sun. Here's 51 Pegasus in relationship to its star. It's very, very close to the sun. So you should keep that in mind. When you're thinking about hot Jupiters, these are planets like Jupiter that are very, very close to their stars. They're not like our Jupiter, which is far from the sun and fairly cold. I want to introduce you to another hot Jupiter, HD 209458b, which for some reason actually got a name, though I'm not sure anyone really uses the name Osiris. Okay. It was the first exoplanet detected through the transit method. Now, Osiris was detected first using the radial velocity method. But after it was detected through the radial velocity method, it was clear that based on its orbit, it was probably a transiting planet. And the folks who detected it using the radial velocity method contacted somebody who probably had a telescope that would be able to test out and prove that the transit method was going to work. I'll tell you about that in a minute. All right, the distance to this star is 154 light years. It's a little further away. It happens to also be in the constellation Pegasus. So 51 Peg was right about here. HD 209248b is over here. It's another star that's like the sun. It's 13% more massive than the sun. It is 4% hotter than the sun. The person that the radial velocity team contacted was right here in town, Greg Henry over at Tennessee State University. And Greg Henry and his team used a telescope that was originally built at built using money at Vanderbilt, but built as a collaboration between Vanderbilt and TSU and put in operation in Arizona. And I'll show you the telescope in a minute. And this is their data. So the brightness of the star is constant, and then boom, the bottom falls out, and it drops down here. And this is the transit that they detected. And the caption to this figure says, photometric observations of HD 209458 from the night of 1999, November 7, show ingress of the planetary transit, the beginning of the planetary transit. They didn't see the whole transit, they just saw the beginning of the transit. And the depth is 0.017, 1.7%. This was an easy one because the planet was so close to the star. The planet's mass is 69% of the mass of Jupiter. The planet's radius is 38% bigger than Jupiter. So the planet is not as massive as Jupiter, but it's bigger than Jupiter. So this is an inflated Jupiter. It's an inflated hot Jupiter. It is so close to the star that it's so hot that it's been puffed up. Its orbital radius is 0.047 astronomical units, so it orbits in 3.5 days. It orbits even faster than 51 Peg. This is the telescope that was used. It was the Vanderbilt, Tennessee State Automatic Robotic Telescope. This is from 1989. Greg is here. Doug Hall, who was Vanderbilt astronomer, is here. Frank Feckel, whose wife is in the audience, was here. They put this telescope together in an operation out in Arizona, and that's pretty neat that Nashville astronomers were involved in discovering this first, or proving that the transit method actually worked for discovering this planet. HD 209458b is a really bizarre beast. It's been studied a lot since it was discovered. The day-side surface temperature is over 2,000 degrees Fahrenheit. This planet is what's known as tidally locked, just like our moon. You know, our moon has a near side and a far side. We only see one side of the moon because the tides, the tidal interaction between the Earth and the moon have locked the moon so it always shows one side to the Earth. That's what's happened to this planet. It shows one side to the star. It never rotates as seen by the star. So the day-side temperature of that planet is really, really hot. The temperature is hot enough that the atmosphere boils off of the planet. Okay? And astronomers have now measured the gases streaming off of the planet, and the rate at which the gases, again, this is not a picture, it's an illustration of what's happening, but this planet is actually acting like a comet with the gases streaming off. 10,000 tons of gas per second boil off into space. Now that sounds like a lot of stuff, and it is a lot of stuff, but this planet is big. At that rate of boiling, it'll take 1 trillion years for this planet to boil away completely. So it's going to be here a while. The tail of this cometary planet is 200,000 kilometers long. That would stretch almost from the Earth to the moon. It's a long tail. A lot of different materials have been detected in the atmosphere of this planet, and that's what's kind of neat. This is what astronomers are now capable of doing. We've detected water, carbon dioxide, oxygen, carbon, and magnesium in the atmosphere of this planet. This is the next step for astronomers, not just detecting the planets, not just saying, we know you're out there, but actually studying the planets themselves, trying to understand what they're made of, what their atmospheres are made of. Because long term, we want to understand if there's life out there. And to do that, we need to study the planets in detail. You may. You probably can, too. Right. Where's this voice? Can we detect materials? Can we detect materials that we can't recognize? I'm going to go with sort of yes and sort of no. Okay. We only know what we know. We talked last week about how we can put light through a prism, spread it out into a spectrum. When we do that, we see these lines, these spectral lines. Those lines are at particular wavelengths, and then we go to catalogs of spectra, and we try to identify the lines. And most of the time, we can say, that line at this wavelength is due to magnesium. That line is due to carbon. That line is due to vanadium oxide. That line is due to methane. There are some lines that have not been identified. So yes, we can detect things that we can't identify. That doesn't mean they're made out of things that we don't know about. It just means no one has synthesized that particular molecule or ion in the laboratory and made it produce light at that particular wavelength, so we don't yet know what it is. But it's probably not a material that doesn't exist on the Earth. It probably is just a material we haven't synthesized in that form yet. But there are definitely signatures in the light of some environments, astrophysical environments, that we have not yet been able to identify yet. Does that answer the question? There was another question right here.
How do they determine that the planet is tidally locked?
How do we determine that the planet is tidally locked? That's a really good question. I think the only way to know at this point that the planet is tidally locked is from calculations. I don't think we can actually see this. It's not like the moon where we can see one side of the moon and the other side of the moon and actually tell that it's not turning. Okay? And I don't think we're able to measure the rotation of the planet yet. Eventually, I think we'll be able to measure the rotation of the planet itself. But I think that the tidally lockedness of this planet is coming from theory rather than from measurement. But I think at this distance, there's no way for it not to be tidally locked. Good question. Other questions? Yes?
Is there any effort right now to find two planets that are relatively close together?
Is there any effort to find two planets that are relatively close together? Yes, and we have lots of them, and we're going to talk about them in a few minutes. Okay. Question was, when she thinks of tides, she thinks of water. And this is not a planet with oceans, so what's the relationship between tidally locked and this planet? All right. Tides not only work on the oceans, but they work on the solid Earth as well. And the tides work on the moon. The moon exerts tides, the Earth exerts tides on the moon exerts tides on the Earth. Planets exert tides on their moons. Jupiter exerts tides on its moons. The tides are gravity stretching objects. Okay? The tides are what physicists refer to as gravitational stretching. So the moon's gravity pulls the side of the Earth that's closest to the moon harder than the moon's gravity pulls the side of the Earth that's furthest from the moon. And as a result, the Earth gets stretched. It's that stretching of the Earth that creates the tides. And even if the Earth had no water on it, the Earth would be tidally stretched like a football in the direction of the moon. And the Earth tidally stretches or deforms the moon so that the moon points like an oblate football stretched with the point toward the Earth. And it's that stretching of the solid moon that keeps the moon pointed toward the Earth. And Jupiter does that to Jupiter's biggest moons, and Saturn does that to some of Saturn's moons, and Pluto does that to its moons. So this happens all over the solar system. Anytime two objects are close enough together, the tides are a differential stretching due to gravity when one side of the object simply is close enough that it feels gravity more strongly because of the pull of a distant object than the other side of that object. Does that make sense? You see the effect on the oceans more strongly than on the solid land. Yes? Say that again, please. Are the tides? Gravitational stretching will happen with any two objects, but with the sun and the Earth, the tidal effect of the sun on the Earth is much weaker than the tidal effect of the moon on the Earth. Because even though the sun is bigger, the moon is closer. But there are always going to be tidal effects. They just will be smaller when the objects are farther apart.
A two-part question. Does the tidal stretching generate heat in the Earth? And two, would that gravitational to heat exchange possibly affect the orbit?
Does tidal stretching in the Earth generate heat? And does that tidal heating, or do the tides affect the orbit? tidal stretching does generate heat. In the Earth, I don't think it generates much heat. In the Jupiter Io system, it generates so much heat that it generates all the volcanic activity on the moon Io. So tides can generate lots of heat. But in the Earth-Moon system, it doesn't generate much heat anymore. Once upon a time, it generated a lot more heat. Does it affect orbits? Absolutely. The moon is spiraling away from the Earth. The moon moves away from the Earth a few centimeters a year, and that's because of the tides. When the moon, long time ago, the moon was much closer to the Earth, and the tides were stronger, and the tides have been pushing the moon away from the Earth over time. And the further back in time we go, the closer the moon was, the stronger the tides were, the faster the moon was pushed away from the Earth. So yes, the tides affect the orbits, the tide affects the spin of the moon, the tide affects the spin of the Earth, it affects lots of things. One more question, and then I'm going to move on away from the tides. There's another question back here, I think. Are all of the hot Jupiters tidally locked? Not all of them, but most of them that are in these 3- and 4-day orbits are. Okay? There are going to be some hot Jupiters in 12-day orbits. They might not be. But the hot Jupiters that are this close almost certainly are tidally locked, yes. Good questions. Keep asking them. I'm going to move on at least one slide. Okay? Because I want to introduce you to another telescope and some other local folks, because I want to give a shout out to all our local folks. Another telescope that has local connections is known as KELT North. KELT stands for the Kilodegree Extremely Little Telescope. Okay? KELT North is in Arizona. KELT South is actually in South Africa. The KELT telescopes were built primarily by Josh Pepper, who his students affectionately call Dr. Pepper. The KELT North was built when he was a graduate student at Ohio State, and then he built KELT South when he was a postdoc at Vanderbilt. He's now a professor at Lehigh University. Other important members of the team include Joey Rodriguez, as you'll see, who's a graduate student at Vanderbilt, but now working with Josh at Lehigh University, and Mark Manner, who some of you may know, who is a lawyer here in Nashville, an amateur astronomer. So why do we need to know about KELT? Well, KELT has discovered some planets. Okay. KELT 2AB, what does that mean? Well, KELT 2A is a star. Capital A means a star in a binary system, and a little b means there's a planet in the KELT 2A system. And it's a hot Jupiter. And it was the first planet discovered by the KELT telescope. This little 8-inch telescope in Arizona discovered a planet. This planet has a mass of 1.5 Jupiters. It's a hot Jupiter in an orbit of 5.055 AU. It's at an orbital distance, or an orbital period of 4.1 days, so it's just like 51 Peg. This star is at a distance of 419 light years. The discovery data is this left panel. You can look at this and say, these guys are crazy. All right? I mean, look at all these data points. And they say, oh, look at that drop there. I look at that and I say, really? Really? You think in that noise you've detected a planet? And they say, absolutely. Look at how that drops. The red dots is their average. You average that data and you see, look, it drops way down there. So they have a whole team of amateur astronomers all over the world that do follow-up. One of those amateurs is Mark Manner here in Nashville. And the plots on the right are light curves made by amateur astronomers around the world who took their telescopes and did follow-up observations of KELT 2A looking for this planet. And it sure is there. Boom. All these astronomers confirm that guy's a planet. That's really cool. They can do this. And they found another one, KELT 6b. Notice there's no capital A or capital B, so KELT 6 is a single star. This is a hot Saturn, which means it's not as big as a Jupiter. It's a slightly smaller planet. This was the third planet discovered by Kelt. Now you look at this plot and you go, really? I mean, really? Okay. There it is. Pretty obvious, isn't it? They say, there it is. That's a planet. Discovered in 2014, just last year. So they sent their amateur team after it, and all these amateurs around the world said, yep, look, there's that light curve, there's the drop. All these contributions from these amateurs around the world, this light curve right here, and this one down here, were made by the Spot Observatory in Nunnally, Tennessee, by our own Nashville's Mark Manor. This planet has a mass of 0.43 Jupiters, which means it's half of Jupiter, a few Saturns. So is it a hot Saturn or a hot Jupiter? Kind of in the middle. Orbital radius 0.079 AU, or it's an orbital period of 7.8 days. So Nashville's in the game. Another planet for you, WASP-12b. WASP stands for the Wide Angle Search for Planets. This is a United Kingdom team. If it was a US-based team, they probably would have come up with a different acronym. Okay? But this is the WASP team. They're now the Super WASP team because they built a bigger telescope. And here's their light curve. This plot is in differential magnitudes instead of absolute brightnesses. You don't have to worry about it, but that's another unit astronomers use. And of course, it's obvious that the light drops a little bit here. Yeah. Okay. So they detected a planet, and there it is. This is a star at a distance of 870 light years. This has an orbital period of 1.09 days. 1 day. This is the hottest exoplanet yet discovered. Okay? In its atmosphere so far, we found carbon monoxide, methane, water, titanium oxide, vanadium oxide, HCN, and molecular hydrogen. This planet has a mass of 40% greater than the mass of Jupiter. Its radius is 70% greater than the size of Jupiter, so it's quite puffed up because it's so ridiculously close to its star and so hot. Its orbital distance is 2% the distance of the Earth from the Sun, 1/44th the Earth-Sun distance. The gravity is so great, this thing is greatly stretched out. It's got this massive, long cometary tail, which appears to have been stretched out into an entire disk around the star. So much is being pulled out from its star, from its atmosphere. Its daytime temperature is over 4,000 degrees Fahrenheit. Its mass loss rate is 6 billion tons per second, and it's estimated to only have a survival time of 10 million years, not a trillion years, 10 million years, which means it can't have been there for very long. Because if it had been there for more than 10 million years, it wouldn't be there anymore. Okay? So somehow it got into this environment and isn't going to survive very long. We don't understand how it got there, but it's not in a very healthy place for it. How many light years away is this one? Was it on the, if it's not on the previous page, then I don't know the answer. 870 light years. WASP-12b. Here's another one for you. Gliese 581. The Gliese stars are nearby stars. Gliese has a planetary system. It's in the constellation Libra. There it is. Pretty exciting star. It's at a distance of 20 light years, which makes it the 89th closest star. That probably won't last because astronomers are busy discovering more stars that are close. But for the time being, it's the 89th closest star. It's a small star. Its mass is 31% the mass of the Sun. Its radius is 29% the radius of the Sun. Its temperature is 3,500 Kelvin, so 60% less than the temperature of the Sun. So it's a cool star. It's a small star. It's a low-mass star. It's not like the Sun. Sort of a red dwarf star. Yes? Who determined the speed of light, and is it an absolute number? Physics determined the speed of light. That's his last name. Joe Physics. Okay. The speed of light was first measured by a European astronomer by the name of Romer in the 1680s or thereabouts. So that's when we first knew approximately what the speed of light was. The speed of light is a constant in a vacuum. The speed of light can be different when it travels through different materials. But the speed of light is the same as, excuse me, as measured by all observers when it's going through a given material. So the speed of light doesn't depend on how fast you're moving, whereas if I throw a baseball out of a car, everybody would measure the speed of that baseball differently depending on whether you're standing on the side of the road or in the car, whereas light is different in that way. But nobody made the speed of light what it is. Physics, the laws of physics in the universe determine what the speed of light is. And because of these objects being 870 light years away, that means we're seeing the light from this object as it was 870 years ago. It took that long for the light to get to us. All right, Gliese 581, which is nearby, 20 light years away. This is a cartoon of the Gliese system in comparison to our solar system. So on the bottom we have the Sun, Mercury in its orbit, Venus in its orbit, the Earth in its orbit to compare with the Gliese 581 system, which has a little star with a whole bunch of planets in a pretty tight set of orbits. So you have Gliese 581e, B, C, G, D, and F. Not in an obviously sensible alphabetical order, right? Yeah. You don't get A because A, capital A is the star. B would be the first one discovered, and then C, and then D, and then E, and then F, and then G. So it's in the order in which they were first discovered. E and B and C, everybody agrees are there. G and D and F are in dispute. Some astronomers are pretty convinced that those planets exist. Other astronomers are less convinced of the data that those exist. So I'm not going to talk about D, F, and G, but I'm going to show you the evidence for B, C, and D. But this is a planetary system, not just a star with a planet. Gliese 581e, let me go back a moment. Gliese 581e is the closest one to the star. So we're going to work our way outwards from the star. Gliese 581e is a super Earth. We're not talking about hot Jupiters anymore. This is a super Earth. It has a mass of 1.7 Earths, 70% more mass than the Earth itself, an orbital period of 3.1 days. So this would be a hot Earth rather than a hot Jupiter. Okay? It was detected with the radial velocity method, so this is the technique. So it's detected just like 51 Pegasus, with the planet going away from us and then toward us. Okay? And very clearly, each data point has an error bar on it, and there's no doubt all these data points are positive velocities and all these data points are negative velocities. The line is the fit to the data, and there's no doubt that it goes from positive velocities to negative velocities. The data is noisy, but look at these numbers. We're talking about half a kilometer per second, 1 kilometer per second, 1.5 kilometers per second. These are really tiny velocities. We're talking about measuring the speeds of the stars moving at this speed. I mean, this is just beyond belief that we can do this. Yes? If the mass is 70% greater than the mass of the Earth, would the gravity on the surface be 70% greater than the gravity on the surface of the Earth? It depends on the radius of the planet. The mass depends on both how much the gravitational pull at the surface depends both on the mass and on the actual size. And we don't know the size of this planet. We only know the mass. If If the object were the same actual size of the Earth, but it had more mass, then the gravitational pull would be stronger. If it had the same mass, but it were inflated, the gravitational pull at the surface could be weaker. So it depends on the combination of mass and size. So this is the evidence for the existence of this planet. It's right. It exists. Is this the perfect fit to the data? If somebody observes again and gets slightly better data, will this fit get tweaked a little bit? Yeah, that's possible. So maybe the mass isn't 1.7, maybe it's 1.6 or 1.8, but this is a super Earth. This is the detection of a planet which is just a little bit more massive than the Earth. This is pretty cool. Gliese 581e.
Using this method, you're measuring the star, right?
Yes.
What ties this one planet to that measure as opposed to the other 6 planets?
The question was, we're measuring the star, so what ties this planet to the star and not to the other 6? Okay. When we're measuring the star, what we actually see is the overall motion of the star. And the overall motion of the star is a complicated set of motions that includes this motion and several other motions. And what you have to do is tease apart the different motions. Okay? So the star's motion doesn't look just like this because this motion is folded together with the other motions that I'm about to show you. And the actual motion of the star is a jumble of all the motions put together. And you've got to be able to tease them apart. But that's doable with mathematical techniques. Yes?
As far as we know, do the masses ever change?
As far as we know, do the masses of the planets change? That would be a very tough thing to do. Unless you had a really big shovel and you could throw some mass off the planet. There's no simple way to change the mass of the planet. Right? So the planets that we saw that were the super Jupiters that were so hot that their atmospheres were boiling off, the masses of those planets are changing. The mass of this planet, it would be hard to change. Because if it's a super Earth, it doesn't have much of an atmosphere. It's really just mostly a solid planet. The Earth, most of the mass of the Earth is the solid Earth. The Earth has an atmosphere, but the atmosphere of the Earth doesn't contribute much of the mass to the Earth. And if you put the Earth this close to the sun, the atmosphere would boil off. And all you'd have would be the solid Earth. And the solid Earth isn't going to boil away. So the mass of this planet shouldn't change. If you took the Earth and moved it to this position, the mass of the Earth would change slightly very quickly as the atmosphere boiled away and disappeared. But after that quick change, then it would stay the same. All right, so this is Gliese 581e. Whoa. I didn't know that was going to happen. All right, here's Gliese 581b, which is a Neptune. It's in an orbital period of 5.3 days at a distance of 0.041 astronomical units, has a mass of about 16 Earths. It's a bigger planet. Here's its radial velocity profile. It goes up and down by plus or minus about 12 kilometers per second. So the actual motion of the star includes this motion plus the previous motions. So what you see is you see this big motion, and you identify it, and you subtract it from the overall motion of the star. And then you discover that there's another one that is the 581e motion. That's meters per second. Yes. Gliese 581c is another super Earth, really super, because it's 5.5 Earths, in an orbital period of 12.9 days. Its motion is about 2.5 meters per second. Now that's about the same motion as Gliese 581e, the first one I showed you, about plus or minus 2.5 meters per second. But this planet is further from the star. in order to make the star move by 2.5 meters per second when you're further from the star, you've got to be a more massive planet. So this is a more massive planet. Because it's in a 12 or 13-day orbit, it's in what's considered almost the habitable zone. Now, for the Earth around the Sun, the habitable zone is where we are, where the temperature is about right for liquid water, in about a 365-day orbit, not in a 13-day orbit. But remember, this star is not nearly as hot or bright as the Sun. So in order to be warm enough for liquid water, you've got to be much closer to this star. And the zone for this star where you'd have liquid water is close to where this planet is. So this planet is near, excuse me, near the habitable zone. Unfortunately, it appears to be just a little bit too close. And the best calculations so far for this planet suggest that it's a little bit too close. And if it has an atmosphere, the temperature is probably a little bit too hot. And it's more like Venus, that the temperature would have run away and it would not have any liquid water on the surface. Okay, let me introduce you to Kepler. The satellite Kepler, and here's the satellite, which NASA launched about 7 years ago, was designed to look specifically in the constellation Cygnus. And these are the target areas in Cygnus for the Kepler field of view. Looking at about 150,000 stars in Cygnus using the transit method to find planets. So all the planets that begin with the name Kepler with a number have been found by the Kepler satellite. Kepler 42 is one of those stars, found in 2012. When it was first found and NASA released this illustration, it hadn't yet been confirmed as a planet, a star with planets, so it was known as KOI 961. KOI stands for Kepler Object of Interest. It didn't yet get to be called a Kepler star with a planet because it hadn't yet had follow-up confirmations with other telescopes. So it was a Kepler Object of Interest. It eventually morphed from KOI 961 into Kepler 42. Kepler 42 has 3 small planets in orbit around it, and the configuration of those 3 planets orbiting Kepler 42 is comparable to the situation with Jupiter and its 4 moons orbiting Jupiter. The dots and the sizes of the objects are not to scale, but the distances are to scale. So these planets orbiting this star are comparable in spatial scale to the sizes or of the distances of Jupiter's 4 moons orbiting Jupiter. It's a tiny, tiny little planetary system. And again, Vanderbilt had a role in this. Here, the 3 Vanderbilt folks who are involved, Professor Kay von Stassen, Dr. Pepper, who you've already met, and Leslie Hebb. Leslie Hebb was a postdoctoral scholar here when they did this work. She's now on the faculty at Hobart and William Smith Colleges in New York State. Kepler 42 is at a distance of 130 light years. It's a tiny little star. It has 13% the mass of the Sun, which means it's just about as small as a star can be and still be a star. Its radius is 17% the radius of the Sun, so it's a tiny little guy. Its brightness is 1/40th of the brightness of the Sun. And here's the data. I want you to look at these numbers here. These are transit measurements. So the brightness here for Kepler 96102 drops down all the way down to 99.9%. Drop of 1/10%. These lines are attempts to fit the data. The fit to the data tell you the size of the planet. The best fit says the radius of this planet is 0.73 Earths. We don't know the mass of the planet. Transit data don't tell you how massive the planet is. The transit data only tell you the physical size of the planet. The wider this transit event is, the fatter the planet. The skinnier the event is, the skinnier the planet. So this planet appears to have a radius of 73% the radius of the Earth. The orbit of this planet, 6/1000ths of an astronomical unit. It orbits in half a day, 0.45 days, less than 12 hours. This second one has an orbital, planetary radius of 78% the radius of the Earth. Again, here's the light curve. It drops all the way down to 99.9%, a drop of 1/10 of 1%. Its orbit's a lot bigger, 1/100th of an astronomical unit. It orbits in 1.2 days. And this third one doesn't drop nearly as far. Its radius appears to be 57% the radius of the Earth. It orbits in 1.8 days. So this planetary system has 3 planets that are all smaller than the Earth. 0.57 Earth radii is comparable to the size of Mars. So this is a different one. So let me not quite go there yet. Okay. So 0.78 Earth radii is comparable sort of to Venus. 0.57 to Mars. These are little guys, 3 Earth-like planets. But these are close to their stars. Now, they're not super hot because this star is not a sun-like star. This is a very interesting little environment. All right. Kepler-37, another system with tiny little planets in the constellation Lyra. Kepler-37b, Kepler-37c, Kepler-37d. B, C, and D. They're in tiny little orbits compared to Mercury's orbit, Venus's orbit, Earth's orbit. They're in tiny little orbits around Kepler-37. This one I wanted to show you because of these plots. All right? These are the transit light curves for Kepler-37. Look at the bottom one first because it's clearest. Here are the data points, and the bottom drops out. And there's no doubt you've got a planetary transit in that one. You can't read very easily what it says here. It says transit depths, parentheses, ppm, parts per million. Parts per million. And it drops from 0 to 100 to 200 all the way down to 600. The drop here is in parts per million. All right? 1,000 parts per million would be 1 part in 1,000, 1/10 of 1%. 100 parts per million would be 1/100th of 1%. These are parts per million. This is just astounding. Now, this one here, again, parts per million. This drop, this is pretty clear. And it's noisy, but that's quite clear. That's a transit. And we're talking about 100, 0, 50, 100. 100 parts per million in that detection. And this one up here, I don't know about this. That's their fit to the data. These points right there, those are the averages. They're pretty convinced. And the averages are pretty convincing. And that's a drop of 20. 20 parts per million. Yes?
Are we talking about parts of a substance per million or just a measurement?
A measurement. We're saying that the brightness of the star is 1,000,000. And as this planet passes in front of the star, it drops to 999,980. And that we're detecting that drop of 20 little bits in brightness caused by the star going in front of it. That the detector is that sensitive. And they're probably right. Okay? There's no doubt they're right about this one, and no doubt they're right about this one. there's no doubt they could detect a drop of 50 parts. 50 would be easy. 50 parts per million. We're not talking about a drop of 1% or a tenth of a percent or a hundredth of a percent. We're talking about a thousandth of a percent. And that's what it takes to detect a planet with a radius of 1/3. 1/3 the radius of the Earth. That's what this top one is. The one down here is 75% of the Earth's radius. The one down here is about 2 Earth radii in an orbit of 40 days. This one 20 days, this one 13 days. But if this one on the top is right, it's the smallest yet known planet with a radius 1/3 of the radius of the Earth. 1/3 of the radius of the Earth is about 2,000 kilometers. There's an object in the solar system with a radius of about 2,000 kilometers. And that would be Mercury. It's a really tiny object. These are tiny, tiny little planets. All right, I want to introduce you to a phenomenon which has been detected among these other planets. And now we're actually going to do some math. You didn't think you were going to do some math in here. Now I'm going to help you out. I'm going to do the math for you. Okay? But I want you to appreciate what's going on here. This is a sketch of Jupiter and its moons. So we have Jupiter, we have the moon Io orbiting Jupiter, the moon Europa orbiting Jupiter, the moon Ganymede orbiting Jupiter. And because of the tides, remember those ugly tides we talked about a little while ago, Io orbits Jupiter in such a way that it completes 4 orbits in almost exactly the amount of time it takes Europa to complete 2 orbits, which is almost exactly the amount of time it takes Ganymede to complete 1 orbit. This is known as an orbital resonance. So let's do the math. Ganymede orbits in 7.155 days. Europa orbits in 3.551 days. So 7.155 days divided by twice Ganymede's orbit is 1.007. When the ratio of one object's orbit, the time for that orbit, to the time for another object's orbit is almost exactly a tiny number, 1 or 2. You've got an orbital resonance. So in this case, the ratio of 7.155 to 3.551 is 2. We've gotten rid of the 2 by bringing the 2 down to here to show that the comparison of 2 orbits of Europa to 1 of Ganymede is 1. 1 orbit of Ganymede to 4 orbits of Io is about 1.011. 1 orbit of Europa to 2 orbits of Io, 1.037. It's about 1. Yes?
Does Callisto validate that?
Does Callisto, the 4th moon, is not trapped in this resonance. It's got an orbital period of 16 days, which is not part of this resonance. So what happened over time is Jupiter captured Io into a resonant orbit with the tides, and then started pushing Io out. And then as Io moved outwards, the tidal reaction between Io and Europa trapped Europa. And then Io and Europa moved out together, and they captured Ganymede. And now Io and Europa and Ganymede are moving outwards together. And given enough time, and that may be billions of years, they would eventually capture Ganymede. The result of the tides in this system generate the volcanoes that erupt on the surface of Io. And the surface of Io is entirely covered with volcanic eruptions. It is so hot, the tides just pump heat into Io over and stretch and deform Io and cause these volcanic eruptions. The tidal heating from Io pushing outwards into Europa don't generate volcanic activity in Europa, but they have so heated Europa that Europa is smooth as a billiard ball, because Europa has lots of water in it, and the heating has heated Europa up so that the water has bubbled up to the surface, and it's all over the surface, and the surface of Europa is smooth as ice, because it is ice. And on most objects in the solar system, you see craters. Think of the moon. You see all these big craters. There's one. Europa doesn't have craters because the craters relax and deform because the surface is warm enough that over time, any crater that forms on the surface of Europa relaxes and flattens out. Europa can't preserve craters for very long because it's too warm because of the tides. That's what the tides do. This is the Kepler-25 system on the left, the Kepler-26 system on the right. In the Kepler-25 system, these are the transits. In the Kepler-25 system, this is Kepler-25b. The transit shows you the light dropping because of the transit from 100% down to 99.95%. This is a small planet. For Kepler-25c, the drop is all the way down to 99.9%. Kepler-25b orbits in 6.239 days. Kepler-25c orbits in 12.72 days. The ratio of 12.72 to 6.239 is 2. 12.72 divided by 2 times 6.239 is 1.02, just like in the Jupiter system. This is an orbital resonance. The tides have captured these two moons, these two planets, into an orbital resonance. The tides from the star with 25b captured 25b and started pushing 25b out, and it captured 25c, and now the two of them are trapped in an orbital resonance, just like in Jupiter's moon system. And in the Kepler-26 system, we have Kepler-26, well, this is 26c, b, and what's called 25003. 25003 doesn't get to be called 26d yet because it hasn't been confirmed. So it's Kepler Object of Interest 250 instead of Kepler 26d. If it really exists, and you see that dip right there, has an orbit of 3.544 days, Kepler 26b 12.282 days, 26c 7.25 days. The ratio of Kepler 26b to 26c, this is a different resonance because it's 3 orbits of 26b to 2 orbits of 26c. That ratio is 1.07. So they're caught in what's known as a 3-to-2 orbital resonance, where one does 3 orbits for every 2 orbits of the other one. There are more of these. There are a ton of these. This is the Kepler-31 system. Kepler-31b. Here we have the transit. It drops down to 99.8%. That one's in a 20.86-day orbit. And 31c drops down to 99.8% in a 42.63-day orbit. The ratio of 2 orbits of 31c, 1 orbit of 31c to 2 orbits of 31b, 1.02. They're in a 2-to-1 resonance. And if KOI 95303 really exists, it doesn't get to be called 31d yet. There's its transit. It hasn't been confirmed yet. It's in an 87.6-day orbit. The ratio of its orbit to 2 orbits of 31c, 1.03. Those two are in a 2-to-1 orbit, which means this one is in a 4-to-1 orbit resonance with Kepler-31b. And we've also got a resonance with this guy, which hasn't been confirmed yet. We have 4 planets in a resonance here. And here's another one in the Kepler-29 system, which is a 9-to-7 resonance. We have Kepler-29b in a 10.33-day orbit. Okay. And Kepler-29c in a 13.29-day orbit. And the ratio of 9 orbits of Kepler-29 29b to 7 orbits of 29c is 1.0076. A 9 to 7 resonance. The tides don't have to trap you in a 2 to 1 or a 4 to 2 or a 3 to 2 or a 4 to 3. Anything's possible. And in this one, it's a 9 to 7 resonance. It's really cool. These resonances are happening all over. The tides are very powerful. Yes?
Does this become a universal, or are there outliers contradicting data?
The tides are going to capture any moons, any planets into resonances which are close enough to the stars for the tides to be strong enough to work, and where the planets are close enough to each other for them to tidally interact. In our solar system, does this happen? Our planets are too far apart from each other for the planets to tidally affect each other. But there are several moon systems in which the planets and the moons have tidally affected each other. All right, Kepler 34. This is a circumbinary planet. In the top panel, the blue points is when two stars, star A eclipses star B, so the light drops way down when star A goes in front of star B. The orange points, I don't do well with orange. I think these ones are orange. The orange points is when star B goes in front of star A. The red points, and there's a red point there, I think. And there's another red point. The red point is when a planet transits star A, and then there's a green point when a planet transits star B. So we have a planet in a binary system, two stars, and the planet is going in front of one star at a time. And in the bottom panel, we have the red dots, a close-up of this point where the planet goes in front of star A. And here is the other red point where the planet goes in front of star A. And here we have the planet going in front of star B. That's kind of cool, a star in a binary system. And here's another one, another star in a binary system. Again, the same deal. The blue points, one star goes in front of the other. And the orange points, the other star goes in front of the other. And then we have a red point. I think there's another red point, and somewhere there's another red point, and somewhere there's a green point, and I don't know where. Okay. But we have the planet going through a transit in front of one star, and going through a transit in front of the same star, and then the planet going through a transit in front of the other star. Circumbinary planets. That's cool. So this is a cartoon of what you have there. You have two stars, and we're looking now, imagining we're looking on top of the system. We have two stars orbiting each other, and then we have a planet out here orbiting the stars. And then in the other system again, we have two stars in orbit around each other, and here's the planet orbiting the two stars. The Earth would be down here at the bottom when we'd be looking up, so sometimes one star would go in front of the other, and sometimes the planet would go in front of one of the stars and then the others. These are both Saturn-like planets. One's 20% the mass of Jupiter, one's 13% the mass of Jupiter. One is in a 288-day orbit. That's like the Earth's orbit. We have a Saturn-like planet in an Earth-like orbit. That Saturn could have an Earth as a moon. This is a neat planet for further study, because we ought to look for moons around that planet, because those moons could be like the Earth. All right, some statistics for you. We try to clean up before we finish here. Some statistics. This is a plot of, it says all known, but it's probably most of the known, because someone probably discovered one this morning. Most of the known transiting planets. This is a plot of the mass of the planet versus how far they are from the star, the semi-major axis in astronomical units. This is 1/10 of an astronomical unit, 1 astronomical unit, 10 astronomical units. So it's a logarithmic plot. The mass in Jupiters up here is 1 Jupiter, 10 Jupiters, 1/10 of a Jupiter, 100th of a Jupiter. The Earth is 1/300th of a Jupiter, so the Earth would be right about here. So for transits, you'll notice that there aren't very many objects down here. Transits, so far, are really good at finding bigger planets which are fairly close to the star. Okay, this is the Earth's distance right here. Almost all of these planets are closer to the star than the Earth is. Most of them are within 1/10 of an astronomical unit. Most of them are really close to the star. The transit method is best at finding stars, planets that are close to their stars. And it's better at finding bigger planets. So all of these planets out here, there must be some of them. And down here, the transit method hasn't found those planets yet. The radial velocity technique, again, the same axes. Here's 1 Jupiter, 1/10 of a Jupiter, 10 Jupiters, 100th of a Jupiter. The radial velocity is finding lots of planets. But you can imagine a line right here. And below that line, we're not finding anybody. Out here, where it's empty, these would be planets that are a little further from the star, that are lower mass. The radial velocity technique is not good at finding lower mass planets that are further from the star, like us. The radial velocity technique is also not good at finding planets down here, below the bottom of the plot, which would be little planets like us, which are close to the star. So these techniques are finding lots of planets, but they're also missing lots of planets. Yes? That's a whole other lecture. Let's talk about that. Let's talk about that after class, okay? Because I want to talk about one more thing. That's a good question. The moon's orbiting a planet, which makes it not a planet. All right. Some brief statistics for you. The Kepler satellite monitored 150,000 stars. Of those, about 42,500 were bright enough to detect Earths. And of those, 603 were detected to have transiting planets. And we have to ask, is that a lot or a little? Of those 603, 10 of the 603 turned out to be Earth-sized planets in the habitable zone. Is that a lot or a little? The question is, what fraction of planets are we missing? We know that the transit technique misses lots of planets because it misses planets that are far from the star. It misses little planets. It more easily gets big planets. So a bunch of people have worked hard to try to figure that out. The transit technique isn't going to detect a planet that doesn't transit the planet. It only detects planets that actually do transit the planet. So what fraction of planets are likely to transit planets? Only the planets orbiting stars that just happen to be aligned just right for us to see it happen. Most stars might have orbits with planets orbiting so that they won't transit. The Earth, if it were 1 astronomical unit from some star, like we are, would cause a drop in the brightness of the star of 100 parts per million. We know we can detect that, just barely. That would be a drop for 12 hours every 365 days. That would be hard to detect. Could we detect it? Well, yeah, if we looked for long enough. Have we looked for long enough? So the Kepler statistics, how much have we failed to detect? The statistics suggest we've failed to detect 92% of the hot Jupiters. We found 8% of them. 92% of the hot Jupiters have gone undetected. 99.5% of the Jupiters in Earth-like orbits have gone undetected, which means for every one of those we've found, 199 of them are in orbits we can't detect. For the Earths in Earth-like orbits, we've detected 1 out of every 2,000, because most of them are in orbits in which we can't detect them. Which means detecting 10 Earth-like planets in Earth-sized orbits is a huge number. Which means of those 40,000 stars, probably at least 10,000 of them have Earth-like planets in habitable zones. And in the Milky Way, of the 400 billion stars, probably at least 40 billion of them have Earths in Earth-like orbits. That's what the data tell us. There are lots and lots of planets out there. And given that, next week we're going to go down the rabbit hole. Okay? We'll start talking about what all of this might mean. And if you really want to know about why the moon is not a planet or is a planet, we can talk about that after class. But I think I'm out of time. So I'll take questions, but I think we're out of time. Okay, thanks very much.